Up to this point, we've figured out how to solve differential equations in a couple of different ways. But really, we only have kind of one method for solving them analytically. And it turns out it's a little frustrating, but there really is no silver bullet for being able to solve every single differential equation that you want. But there are tricks for solving certain types of them. So we need to be able to categorize differential equations. And the first way that we're going to really kind of categorize is as separable or not separable, if you remember from section 1.2. Another way we might categorize things as whether they are linear differential equations or not. And you might see linear and think y equals mx plus b, kind of throw back to your algebra days. You're not too far from the truth there, because a linear differential equation is any first order, it's got to be only first derivative, differential equation that can be written in the following way. Now notice, this is our differential equation is a function of t and y. And y is the dependent variable and t is the independent variable. And so we're saying the derivative, dy dt, is equal to some function of t times y, but it's just y to the first power plus another function of t. So I want you to recognize really what we're doing here is it's like we're multiplying something times y plus something else. And so if you think back to your y equals mx plus b, the m in this case, the slope is this thing right here, and the b in this case is your b. So it's kind of similar in format to what you're used to when you're thinking of a linear equation. And these get used all over the place. There's tons of applications for linear differential equations. They get used from everything from heating and cooling systems to radioactive decay to finance to mixing solutions, mixing gases. They get used all over the place. And so it's a really good place to start when you're modeling with a mathematical equation, differential equation. And so what we need to be able to do is kind of recognize when we're faced with a linear differential equation or not. So we've got three examples here, and the question is, are these examples of a linear differential equation? So in the first case, take a look at it, and you can see it looks like we have something times y plus something, right? In this case, you can say your a of t is equal to t squared, and your b of t is equal to cosine t. And that's perfectly legitimate. Notice they're both a and b are both just functions of t, and in this case it works out just fine. And of course it is linear. What makes it linear is the fact that y is to the first power, right? This is y to the first power. So y is to the first power. So that makes it a-okay. And in the second case, you'll notice it's a little different, but we have to have it written in this form in order to do a direct comparison. So I'm going to have to renegotiate this a little bit here. And so I'm going to rewrite, this will become dy dt equals, I'm going to move the 3y to the other side and group it together with this guy right here. We'll wind up with t plus 3 times y plus 2. And in this case, it's pretty easy to see there's a function of t sitting in front of the y. That's my a of t. And then this guy right here, even though it's a constant, technically that's my b of t. It's a function of t. It's just 2 times t to the 0th power, right? And of course, y is to the first power again. So it works. It is a linear differential equation. And in the third example down here, I'm going to scoot this up a little bit more. You can see that you have dy dt equals 2y plus 8, and in this case, both of our multipliers here, the a and the b, are both constants. And so this is a really simple case where a and b are both just constants, right? And this one you probably recognize right out of the gate. Wow, we could totally solve this. That's the type of equation we've been able to solve up to this point, right? Or a variation on it. So let me give you some examples that are not linear, and we're going to explain why they're not linear. In the bottom, in this first case, you're like, oh, it's just something times y plus 0. It's just 1 times y plus 0, so that's not a problem. But the tricky part here is the dependent is to the second power, right? The dependent variable is not to the first power, which makes it not linear. Wah, wah. Anything other than 1 in that power, and it doesn't work. How about in this case? Now we're not talking about dy dt, it's dz dt. So you've got some function of t times sine of z, but there's the problem. It's not just z, it's the sine of z. And so it's not that the z, the dependent variable, is raised to a strange power. It's that the dependent variable is within the sine operator. And that's what makes this not linear, right? And so something like this, we wouldn't be able to use the techniques of this section to be able to solve it. And so what are the techniques of this section? Well, we're going to get to it. We've got one more kind of description, definition that we need to sort out here. And so on the next page, you'll see a little bit more terminology. This page says, okay, there's really a breakdown. If you have a linear differential equation, it comes in 2 flavors. So you can think of all linear differential equations break down as either what's called homogeneous or non-homogeneous. And there's another word for each one of these. Sometimes these are referred to as unforced for homogeneous or forced for non-homogeneous. And that's going to make more sense later on in chapter 2 and chapter 3 once we get into a little bit more applications of these things. But notice the homogeneous, the defining feature of a homogeneous differential equation is that the b of t, that second term, is equal to 0. Let me flip this around, make sure I got it right. The b of t is equal to 0, and for the non-homogeneous, the b of t is not equal to 0. Now, it's a small thing, but the word is not homogeneous. It's homogeneous, right? The word homogeneous technically is no longer used in any context anymore. So you might think of, homogenized milk and things like that, but it's actually not spelled that way. It's homogeneous. And so let me give you an example of a homogeneous, unforced linear differential equation. It's something times y, but there's no extra term. There's no second term over here. And over here for a non-homogeneous, all I have to do is just add another term. So it's y plus something else, right? So if there's multiple terms, there's a good chance that you're talking about something that's non-homogeneous, but it really boils down to whether that function of the independent variable is equal to 0 or it's something else. So there's a kind of a special case situation that you probably have already recognized. If your a of t is a constant, it's a coefficient, we call that a first order linear differential equation, has a constant, as we call it, a constant coefficient equation, something that looks like this, where lambda in this case is a constant. And those are the simplest, those are the super easiest to deal with. And if you make b 0, you can recognize that right away as being, oh, that's just an exponential growth or decay situation. And that's the simplest kind of differential equation. That's why we started with that way back in 1.1. So we're going to start with the homogeneous case, the case where it's really only one term on the right-hand side, and it's a multiplication of some function of t times y. And when we do that, we have this homogeneous case, homogeneous case. And we're going to start with what's called the linearity principle. And this is one of those mathematical statements that's always true, but it's written in the form of an if-then statement. So look for the if. If we know one solution to a homogeneous differential equation, then any constant multiple is also a solution. And so sometimes this is referred to as the constant multiple rule, right? If you know one solution to a homogeneous differential equation, then you know any solution because you just multiply it by a constant. And so in a more mathy way of saying this, we might say over here, if y sub h is a solution, then k times y sub h is also a solution. And so we're actually going to kind of prove that and see what it looks like when we do it. So notice it says for any constant k, and that means for literally for any constant. And that could be any real or complex constant. Now, up to this point in your mathematical careers, you've kind of studied a little bit of complex numbers, but you've stayed clear of it. Most calculus up to and through Calc 3 doesn't really deal with complex numbers. And that's okay, but we're actually going to dip our toes into complex numbers later on. So I point this out here. Any constant, whether it's real or complex, that's still going to hold true. So why is this true? Well, let's verify. Let's see how this works. So we're going to start with our differential equation. We've got dy dt equals some function a of t times y. If that's the case, and let me get a different color here, and we know that y with a little subscript h of t is a solution, right? It's given. The question is, what happens if I multiply that solution by a constant? So let's check. Let's check and see what happens. We're going to check on some constant k times y sub h of t. So we're going to do that by taking our equation, and of course you can verify a solution for a differential equation the way you verify a solution in mathematics. You substitute things in. So I'm going to substitute this thing right here in for y here and here in the differential equation. So I'm going to write it in using little multiple colors here. I'm going to take the derivative with respect to t of k times y sub h of t. Twink. And ask, is that still equal to the function a of t, whatever that happens to be, times y sub h of t. So we have to do a little fancy footwork here, but when I multiply this, oh sorry, I forgot my k. I'm sticking it times k, times k. So when I multiply it through, I have to see how this works. I'm going to take the derivative of this side, and I would have k times d dt, the derivative with respect to t of y sub h, right? And on the right hand side, I'm going to pull the k out front, k times a of t times y sub h. Now, if you're paying attention, you might notice that the k's on both sides are really kind of redundant because they're just going to wind up getting canceled out. So let me grab a different color marker here so we can do that. So the k and the k, those get canceled out and those become 1s, right? And what we're left with is the derivative of the thing that we know is a solution. Is that equal to a times the solution? But guaranteed, if it's a solution, then it makes this equation true. So the fact that we have dy sub h dt equals a of t times y sub h, that's exactly what you would get if you just plugged in your solution into the original differential equation. So this is just true, right? So that means any constant times y sub h of t must be a solution as well. So it's a small little proof. I mean, there's not much to it, but we're basically verifying that if you multiply any constant multiple times a solution, but remember, of a homogeneous linear differential equation. So it only had this one term on the right-hand side, right? Some function of t times y. If you multiply a solution by a constant, you get another solution. So that's pretty handy to have. So on the top of the next page, you'll see we're going to kind of take some notes from this and then wind up applying it to a particular problem.